In the tutorials on the VAR model, we use the Canada dataset from the VARs package in R to illustrate the application and estimation of the VAR model along with several goodness of fit statistics. We will continue with the same Canada dataset to illustrate the estimation and interpretation of impulse response functions, or IRFs. Moreover, we will focus on orthogonalized impulse response functions, that is, we will incorporate contemporaneous effects and allow some variables to affect others in the same period. Even though we estimated a reduced-form VAR model without contemporaneous effects in the earlier tutorials, we can still estimate orthogonalized impulse responses from that reduced-form R and Stata and by using the IRF function provided by the VARs package in R. The Canada dataset has 4 variables including E for employment, PROD for labor productivity, RW for real wages, and U for unemployment rate. These variables were ordered as E, PROD, RW, and U in the dataset, and we will proceed with that ordering in our example. Under the Cholesky decomposition discussed in the IRF theory tutorial, the ordering of variables determines which variables will affect others contemporaneously. Here, employment or E has been ordered first, hence, it can affect all variables including itself in the same time period. The other variables PROD, RW, and U cannot affect E or employment contemporaneously. Similarly, PROD is ordered second, so it can affect only itself, RW, and U contemporaneously. Since E is ordered before PROD, PROD can affect E in the next period only and not in the same time period. However, E can affect PROD in the same period. The same logic applies to RW and U as well. RW can affect only itself and U contemporaneously or in the same time period because it is ordered before U. Finally, U can affect itself in the same period and cannot affect any of the other variables contemporaneously because it is ordered last, that is, U can affect E, PROD, and RW only in the next period after a lag. In R, we can use the IRF function provided by the VARs package to estimate impulse response functions. Suppose we wish to analyze the effect of shock to PROD or labor productivity on employment E and PROD itself, then we can use the IRF function as shown here. Here, IRF PROD will store the results of the impulse response functions, and the var2 object contains the results of the reduced form var of order 2 or var2 model we estimated using the var function provided by the VARs package. The option n.ahead is used to specify the number of time periods we want to estimate the impulse responses. n.ahead equals 12 implies that we want to estimate the IRFs or trace the effect of the shock for 12 time periods. Since we are using a quarterly dataset in our example, this means that we will analyze how the effect of shock will evolve in the next 3 years. The option ortho can be used to specify whether we wish to estimate orthogonalized impulse response functions and include contemporaneous effects. Specifying ortho equals true means that the function will include contemporaneous effects and the ordering of the variables will be the same as they are ordered in the dataset. If we wish to change the ordering of the variables, we have to order them in a different sequence in the dataset before estimating the VAR model. The option impulse is used to specify the variables to which the shock will be delivered. For example, if we wish to study the effect of shock to PROD, then we will specify impulse equals C PROD. It is important to note here that we can specify multiple variables in the list if we want to estimate the impulse responses for multiple variables. For instance, we can specify impulse equals C PROD E to estimate the IRFs for labor productivity and employment variables. The option response is used to specify the variables whose response we wish to analyze. For instance, we wish to study the effect of a shock to PROD on employment E and PROD itself. In such a case, we know that our impulse variable is PROD because we are delivering a shock to labor productivity, or PROD. Our response variables will be employment E and PROD itself because we wish to study how these variables will change in response to a shock to PROD. Moreover, we can specify other variables in the list as well if we want to analyze the response of more variables, such as RW or U. The CI option is simply used to specify the confidence coefficient for the confidence intervals for the IRFs. When we plot the IRFs using the plot function, the confidence intervals will also be plotted along with the impulse responses. Stata has a set of commands or functions to create, manage and graph impulse responses. The first step is to set an active IRF file using the IRF set function. It activates an already existing IRF file or creates a new one. We specify IRF set IRF Canada to create a new IRF file. Next, we estimate the impulse responses using the IRF create function. This will estimate the impulse responses, orthogonalized impulse responses, and several other statistics. Here, we save these impulse responses under the name Canada 12 within the IRF Canada file we created earlier. The step option is used to specify the number of time periods up to which we wish to estimate the impulse responses. Step 12 implies that the function will estimate and trace the effects of shocks for 12 time periods. The order option is used to specify the order of variables which is important for estimating the orthogonalized impulse responses. It will include contemporaneous effects by applying the Cholesky decomposition by default. The benefit of this option is that we can change the order of variables without having to estimate the VAR model again with a different order. In our example, we will proceed with the default order of employment, labor productivity, real wages, and unemployment. After estimating the IRFs, we can use the IRF graph function to plot the impulse responses. In this function, we specify OIRF to estimate the orthogonalized impulse response and include contemporaneous effects. Instead of OIRF, we can also estimate several other statistics such as simple impulse responses using IRF, forecast error variance decompositions using FEVD, and more. We saved our estimated impulse responses under the name Canada 12, so we specify Canada 12 in the option IRF. The options of impulse and response work the same as in R. We use these options to specify the variables to which we deliver the shock and the variables whose response we wish to analyze. Let us suppose that we want to study the effects of shock to labor productivity prod on employment, E, and labor productivity itself. In such a case, we can specify prod in the impulse option and E and prod in the response option. We can also specify more than one variables in these options to graph IRFs. For example, we can specify E and prod in the impulse option and specify E, prod, and RW in the response option. Then, we will obtain the graphs for orthogonalized IRFs where the shock is delivered to E and prod, and we study how E, prod, and RW respond to those shocks. The level option is used to specify the confidence coefficient, and the confidence intervals for IRFs are estimated based on this option. Here, we specify 95 as the confidence coefficient, which implies a 5% level of significance for the confidence intervals. In a stationary VAR model, the impulse response functions converge back to zero after some time. This is because of the stability condition and how we derived the impulse responses in the tutorial on IRF theory. Hence, the effects of shocks in a stationary VAR model are not permanent. That is, the shocks are temporary or transitory. In a VCM model, however, the shocks can be permanent because we have non-stationary variables in a VCM model. In the VAR model in our Canada example, we can estimate the orthogonalized IRFs and include contemporaneous effects in R and Stata. Let's take a look at one of the orthogonalized IRFs generated from our Canada example. In the IRFs shown here, prod or labor productivity is our impulse. That is, we are analyzing the effects of shock to prod. The variables employment or E and prod itself are our response variables. That is, we are studying how employment and labor productivity will respond to a shock to prod. Moreover, we have plotted the orthogonalized IRFs for 12 periods after the shock is delivered. Remember that we chose to order employment E before prod. That is, prod cannot affect employment in the same time period. But prod can affect itself, RW and U, in the same time period. This ordering is evident here because the IRF for variable E starts from 0 when the shock to prod is delivered in time period 0. On the other hand, shock to prod instantaneously affects prod itself, as we can see in the bottom IRF graph. A 1-unit positive shock to prod increases prod by approximately 0.7 units in the first period, and the effect is maximum in the first period or 1 quarter after the shock. The effect of shock declines after the first quarter and converges to 0 by the 12th time period or after 3 years, since we are dealing with quarterly data. We can also see that the effects are significant because the 95% confidence intervals are above 0. However, the confidence intervals are above zero for the first 5 quarters only, beyond which the impulse responses may not be significantly different from zero. In case of employment, a 1-unit positive shock to prod increases employment gradually over the quarters, and the effect is near maximum after 1.5 years. The 95% confidence intervals are above zero for the first 1.5 years and indicate that the effects of shock to prod on employment are significant. The impulse responses start converging back to zero after 2 years. If we plotted the IRFs for more time periods, we would see them converge to zero gradually in 5 years. Thank you for watching, and I hope you liked the tutorials.